Hello everybody, we are still talking about the boundary conditions, and in this video we are going to talk about the types of boundary conditions. So this is important because you need to understand what are or what is the form of a boundary condition, how I know that it is a boundary condition, and how can I tell from the information that I know that this is or this information can be translated into a boundary condition or not. So as we said before, the boundary conditions are the conditions that we know and that are related to the dimensions or the space. So it's mainly, in maybe 90% of the cases, it is related to the points of beginning and the ending of the diffusion. Sometimes it's some point in between the beginning and the ending of the diffusion, but it's an information at a specific point that you know at the beginning of the diffusion, at the end of the diffusion, you know the concentration, you know the flux, you know anything that is a useful information that you can use with the continuity equation after integration. So we can group the boundary conditions that we usually see into four types, or four groups. The first is the boundary condition that is related to the concentration at the boundary. So here it is a concentration. I know the concentration, not a flux, not rate, not anything else. It's the concentration itself. I can know what the concentration is at the boundary. The second is related to the reaction that takes place at the boundary. The third is related to the flux equals 0 at specific points. And the fourth is related to the convection mass transfer at the boundary. So we'll go through these in some details now. So we will start with the first type, which is related to the concentration of a transferring species at the boundary is specified. And here we have different cases. So the first case is the simplest case if it's already specified that the concentration equals a specific value. So let's say the diffusion is taking place from this point into this point, from x equals 0 to x equals L, and I tell you that there is a gas stream here that is continuously passing, and it's keeping the concentration of species A at this point equals a constant value. So this is gonna be it. So you know that at x equals 0, the concentration equals CAS mole fraction, the density, whatever, I mean the mole mass concentration, molar concentration, anything, any information related to concentration as this interface. And this is the easiest case of all. In other cases we don't have this information, but we know some information about the system itself, and from our understanding of the system we can tell the boundary conditions. So for example, in a case of let's say this is a cup of water, and this is water that is I mean there is air touching the surface of the water. So this interface is facing air from one side and water from the other side, and the water vapor is diffusing from this surface to from x equals 0 to x equals L, and this is the diffusing distance. This is where diffusion takes place. So I can tell, because this is pure water and there is nothing else here, so the partial pressure of water at the surface equals to the vapor pressure. This is something that we discussed earlier in the first chapter when we talked about the vapor pressure, and we can easily tell that this is the concentration at the surface. So this is in the case of a gas contacting a pure liquid. This can be similar to other cases. For instance, if you have a solid that is contacting a liquid. So again, let's take a look at this, and let's consider this as a cube of sugar that is immersed in water. So let's imagine there is a cup of water and there is a cube of sugar that you dropped in the water, and this cube of sugar is dissolving in water. So sugar is dissolving. So the concentration of sugar away from the cube is low, maybe at the top of the cup, and at the bottom of the cup where the cube of sugar is, the concentration is maximum, which is logical. So we can tell that the concentration of sugar at the interface, which is the interface is the surface that is touching sugar from one side and touching the water from the other side. So the concentration of sugar here is going to be the maximum value, the maximum positive value of the concentration of sugar in water, which is the maximum solubility, or we call it the solubility limit, and we give it a symbol C star, Ca star. So this is in these two cases we have pure liquid like water with air, or pure solid in liquid like sugar in water. There are other cases which are similar, but in these cases we don't have pure liquid like water in or contacting air. In these cases we will have a mixture of two liquids. So if you have two liquids that are in contact with each or are totally miscible with each other, and they are exposed to air, and you still want to see, let's say this mixture is benzene and toluene, and you want to see how the benzene would evaporate, what is the rate of evaporation, the flux, whatever. So you need to know the partial pressure of benzene at the interface. In this case it's not pure benzene. If it's pure benzene, then you can say it's partial pressure of benzene equals to the vapor pressure, but it's not pure benzene, it's a mixture of benzene and toluene. So the law that we can use is called Raoult's law. This is valid for ideal systems. Like benzene and toluene, they have similar molecular structure. They have no hydrogen bondings or anything that will lead to a non-ideality in the behavior. So they are close to a very ideal mixture. So in this case, you can apply Raoult's law, which states that the partial pressure at the surface of benzene equals its mole fraction in the liquid phase multiplied by the saturation pressure. And this is a pretty simple equation, and you can then go back to the previous case if you have pure benzene. So if it's pure benzene, then X equals 1, and then the partial pressure equals the vapor pressure. So this is a case that you can use and confirm at the case of X equals 1. So this is the third case. The fourth is similar, but in this case we have a gas that is slightly soluble in water or in the liquid. So in this case, in the third case, we had two totally miscible liquids, but here I have a gas that is dissolved in a liquid. In this case we can use a law that's called Henry's law, and Henry's law is valid for low concentrations. It's not valid for high concentration. It's, I think, for X equals or less than 5%. So for these low concentrations you can use Henry's law, which is a very simple law. It's exactly like the Raoult's law, but instead of saturation pressure we use Henry's constant, which we can get from tables like this. It gives you the Henry's constant for gases in aqueous solution, meaning in water, and it gives you the value of H, which is this, at different materials at different temperatures. So you can say that the carbon dioxide has Henry's constant of 1300 at 290 Celsius, and you can directly substitute in this equation to get the partial pressure of carbon dioxide at the surface of water. So this is the fourth case. The last case is similar, but in the case of gas, but it's not dissolving in liquid, it's dissolving in solid. And this is a case that happens, that there are some solids that are permeable to gases, which means that the gas can dissolve in the solid itself. It's not diffusing in the pores inside the solid, it's diffusing in the solid itself. And this is something we can imagine it here. You have a balloon that is filled with a gas A, and this gas A is soluble in the balloon, so it diffuses through all the walls of the balloon, and the balloon has thickness, so the concentration of A is high at this side, which is the inner side of the balloon, and low at the other side of the balloon. So while it's diffusing, its concentration decreases, and the maximum concentration would be on the side that is facing the gas. So this is the maximum concentration, which is CAS, and this CAS can be got from an equation that is or contains a parameter that's called the partition coefficient or solubility constant. So it tells you how the concentration would be at what partial pressure of the gas. So if the partial pressure increases, the concentration will increase, which is logical, but the material has its role as well, which is here in this parameter S. This parameter S can be found in tables like this, where you can see oxygen in natural rubber at 298 will have the partition coefficient or solubility constant of this. If it's hydrogen in nickel at 358 Kelvin, it's going to be 9.1. So it's not something difficult. It's just an equation that you use to specify the concentration at the interface for a gas that is diffusing through a permeable solid. So this is the first type. The second type is related to a reaction, and here I would like to distinguish between two cases, and these two cases are very similar, but they're not the same. These two cases are when you have a reaction that takes place at the interface. Let's say there is a catalyst or something where the reaction takes place on. And what you have here is A and B are diffusing from x equals 0 to x equals n, so they are going in this direction until they reach the surface. The reaction takes place and they produce C. The other case is A and B are diffusing together from x equals 0 to x equals L, but the reaction is taking place while they are diffusing. It is taking place during the diffusion. It's not at the interface, it is during the diffusion. So it's important to understand this difference, because this will be translated in two different ways when we translate them into equations. So to understand what we should do, we need to go back and remember how we dealt with the derivation. So we had this small cube in space, and we said that the mass in, mass out, the accumulation, and the reaction, they are all terms that are taking place in this small cube. And then we integrated over the whole space, which is the distance where the space where the diffusion is taking place in. It's not on the interface, it is the diffusion distance itself. So based on this, we can say that in this case the reaction term is not zero, because here the reaction is taking place while the diffusion is taking place. It's not at the interface. But here at the interface, it's not the same. We don't have any reaction taking place here. The reaction is a boundary reaction. It happens at the boundary. So in this case, the reaction is a boundary condition, okay, because the reaction takes place at the interface. But in this case, the reaction is not a boundary condition. It is a term that I will put in the continuity equation. And here the R equals 0 in the continuity equation. It doesn't mean that I don't have a reaction, but I don't have a reaction during diffusion. The reaction is at the interface. So I hope this point is clear. When we have a reaction, or the boundary condition is a reaction, then we have three options. The first option is to define the fluxes of different species from the stoichiometry of the reaction. So I know that from the balance of the equation that A reacts with 2B to produce 3C. So the flux of A equals, or of B is double that of A, and the flux of C is triple that of A. It's 3 times that of A, but I have a negative sign here. And the reason is that the flux of A and B are from 0 to L, and the flux of C is from L to 0. So A and B here are getting consumed, so their concentration is small, and C is produced, so its concentration of high. So C would go from high concentration to low concentration, and B would go from high concentration to low concentration. So that's why we have this negative sign here. The second case, if I know the kinetics, and the kinetics is the reaction or the equation that describes how the reaction rate is affected by the parameters that affected it include the effect of temperature, the pressure, the concentration. Whatever factor that affects the reaction is included in this rate equation. One very simple case of a rate equation is what we call the first order reaction, which is just a constant multiplied by the concentration of the reactant power 1. We call it first order because it's raised to the power of 1. And here we put the flux at x equals L equals negative the rate, which means that the flux going in equals the rate of reaction. and we put negative because A is consumed. So it's obvious here. The last case is the simplest case if we have a very quick reaction, and in this case the quick reaction means that any molecule of A that reaches the surface will automatically react in no time, and this means that the concentration of A at the surface will be 0 because A cannot stay there, so its concentration is always 0. The third case is related to the flux, which is or which are cases when the flux equals 0, and this can be achieved in or this takes place in two cases. First, if we have an impermeable interface. So we said earlier that there might be a solid material that has permeability to a gas, but it might be impermeable to other gases, so it's not allowing another gas to diffuse through it and go from the other side. So if a gas is diffusing through a phase and then it faces an impermeable interface, so this impermeable interface is not gonna let the flow go, so the flux of this material or this gas through the impermeable surface is 0. So this is what we say here, that the flux at x equals L of an impermeable interface equals 0. And for the last case, if we have an excess of symmetry, so let's say we have two rods here or two plates, and these plates contain a material that is diffusing. The concentration here equals the concentration here. The dimensions are the same. So this line here, the dotted line, is an axis of symmetry. So whatever is beneath this line is identical to what you have on the or above this line. So there is a symmetry, and at this axis of symmetry there is no reason or there is nothing that will make one flux be more than the other. So the flux from the two sides is the same. So there is no flux at this point. So flux coming from here equals to the flux coming from here. So the gradient at x equals 0 equals 0 as well. The last case is if you have convective mass transfer, and by this we mean, for example, you have a cup of water where this is the surface of water. Water vapor is diffusing from the surface of water to the upper surface of the cup. All this is molecular diffusion, but above the cup there is a fan or something that is making a flow of air above the cup. So the water vapor that is going from this side of the interface to the other side is swept by the convective mass transfer. So the rate or the flux of the of water vapor going to this interface equals the flux coming out of this interface, and the flux coming out of the interface can be calculated from the convection mass transfer equation, which is K multiplied by CAS minus C infinity. So these are the four boundary conditions, or four types of boundary conditions that we see. It's gonna be clearer when we solve problems, and we will see how we can use these boundary conditions. But we need to have an idea of what a boundary condition means, and this is what I tried to do in this video. In the next video, we'll see how to put everything together. We have already talked about the equation, we talked about the boundary conditions, the special cases of the equation, and now we want to see what is the strategy of solution, which is an important thing. So this is the topic of the next video, and I'll see you then, inshallah. Goodbye.